Yeah.
Okay.
Okay. So welcome again in this edition of the Motivic geometry seminar. Joseph Ayoub will talk about Anabelian representations of the Motivic Galois group. So.
All right. Okay. Thank you very much for this opportunity to speak in this seminar. All right. So I want to report on some recent work. I mean, I think I've been thinking about this maybe about 2 years now, yeah. So it's about the Motivic Galois group and its action on some object somehow of Anabelian nature, like fundamental groups of some Abelian or some algebraic varieties. Right. So I will basically divide my talk into 2 parts. So the first part will be probably longer than the second one, and in the first part somehow I will somehow tell you about the overall picture, and state two theorems. And in the second part, I will say a few words about the proofs. So sorry. Oops. The overall picture. So that there are two players that I need to introduce. They are basically kind of well known. So the first thing I want to introduce is somehow the notion of sheaves of geometric origin. This is a very classical notion, but I want to make this very precise. So this is sheaves of geometric origin. And before I forget, let me also say from the beginning that I will be focusing today on the Belyi version of this of the story. So I will be always so I have a field K and embedded into the complex number, and so I will be looking at the Belyi version of this. And so what I will say will have also an analytic version that works in characteristic P also, but of course with some modification probably. I have to say that I haven't thought very carefully yet about the picture in characteristic P, but I'm confident that many things are still true and can be proved. Okay, so so sheaf of geometric origin in the Belyi setting. So what are these? So let us take X a variety over K. So finite type scheme over K, and so I want to introduce a category of sheaves of geometric origin. So I will denote this by sheaves geometric X, and so I'll be using the somehow the convention or the language of infinity categories. So I will first put a heart here to say that I will first tell you what is the Abelian version of this category. So so this is it will be a subcategory of sheaves on X analytic. So X analytic is the analytic variety associated to X. Again, say with a heart here. So this is the subcategory generated, or let's say the smallest subcategory containing the following objects. So the R, I, F lower star will be analytic. And I will work also with rational coefficient. Again, this is not necessary, but just to simplify a little bit my life. So by this guide, where F is some morphism from Y to X, seem to be proper. Okay, so containing this, and I want this to be also.
Joseph, sorry to have interrupted you. What topology do you consider on the right-hand side sheaves of X analytic? Just to recall.
The usual topology. The usual topology.
The usual topology. Okay. Thank
you. And so I take push forward for the analytic topology. I want this to be so F proper. It's not necessary, but again proper, and I want this to be also stable or and stable by kernels, co-kernels, extensions, let's say, and also and filtered co-limit. Okay, so this is what I will call. So an object of this category is called a sheaf of geometric origin. And then, of course, so this is the heart of some stable infinity category, which I will denote by sheaves geometric. So this will be subcategory of sheaves on analytic whose objects are sheaves such that the homology belongs to is of geometric origin. Is of geometric origin in the previous sense. Okay, so this is again, I mean, I think this is something that everybody knows, but as far as I mean, there are also, of course, in the literature some precise definition of this, but anyway, so this is what I will take as a definition of sheaves of geometric origin. This is the first kind of main player of this talk, and the second, or maybe before going to the second part, let me also introduce some more notation. So I will also considering or also be considering the category of local system of geometric origin on X. So this will be defined as the full subcategory of sheaf of geometric origin. So full spanned by the dualizable object. Okay, so it's these are the local systems, and it's yeah. So I said dualizable object, but you can also say that the homology is a local system. This is the same. And I want also maybe to close, but yeah, maybe not. Okay. All right. So these are the some notation now. The second player is the Motivic Galois group. Let me say a few words about this. So I'll denote by Gmot. And if I want to be precise, I would say also Gmot K. So this is the Motivic Galois group. Of the field K, which is associated to the complex embedding, right? So it depends on, right, so associated to the fixed embedding into C. Right. So what kind of object this is really? So in fact, I want to consider this as an affine derived group scheme. Right? So this is naturally an affine derived group scheme over Q. It actually can be defined over Z or even over the sphere spectrum, but let's simply, I will consider this over Q. And right, so it's so differently, really, this is really the spectrum of some some Hopf algebra, which a priori might have some. So it's connected. It is a spectrum. Say of IE. It is a spectrum of a connective Hopf DBG algebra. But which a priori might have some positive homology. So it is conjectured that this is not the case, that this group is actually a classical group. But since we don't know this yet, somehow I will have to consider it as a derived scheme, at least for the theorem to be true. So I need the whole structure. Let me also, I mean, I didn't give a definition yet of what this is saying. So one way to think about this, and this is somehow the way that I will need later, is as follow. So you can take as a definition for this as following thing. So consider, we'll call it maybe B curly. This is an object. So it's a commutative algebra in the end. Okay. This guy is so the algebra representing the algebra representing singular cohomology on motives, and so then this G mod is very simple. It's just simply the group of automorphism as an algebra. So you can take this as a definition, and this is enough for what I want to say. So right, so it's so if I want to be very precise, I would rather say that so this is really in fact this is really the group of Q valued point of this guy, but yeah, it's easy somehow to make this also. So maybe I put an underline here to say that I consider this was its natural structure of a pre-stack on yeah. Okay. Anyway,
so sorry,
maybe are the automorphisms as algebras or as?
Yes, as
okay. Thank you.
Mm-hmm.
So, sorry, what do you mean when you say it's the algebra representing singular cohomology?
What do I mean by this? In the sense that if you take yeah, so if you take morphism from a motive to B, you get the singular cohomology of M.
So it would be like a linear version of the Motivic spectrum representing singular cohomology.
Yeah, it is the Motivic spectrum representing.
Okay.
Is, yeah. It is. I mean, maybe you are confused about me writing DM, but you could write SH also.
Yeah, that would be more clear.
Yeah, okay, it's the same. It is the Motivic spectrum representing singular cohomology. Okay. All right. So yeah, I think it's enough for this. Okay. So and then now I can state the first theorem. So I call this theorem 1. So it states simply the following. So there is an equivalence of derived group pre-stacks between the Motivic Galois group and so the pre-stack of automorphism of the functor that sends a variety X to the infinity category of sheaves of geometric origin. So I write it like this. So I put this blank to say that this I consider this as a functor on varieties. So, and I want maybe to take this with the monoidal structure. Okay, so this is the theorem, and let me maybe say a few words about the right-hand side of this equivalence. Right, so maybe remark. So yeah, the right-hand side, it's kind of it's kind of a complicated object to think about. But if you want, as a first approximation, you could think about this as a space of families of equivalences of. So let me write it. Okay, so an object or an element, I don't know, an element. I don't want to say. Sorry, let me. Okay, an element of the right-hand side is a family. Is roughly speaking a family theta x, which is indexed by schemes of finite type over k, where theta x is an equivalence of the category of sheaves of geometric origin on X, respecting the tensor product. So it's monoidal equivalence. Right? So it's some kind of an equivalence like this. And of course, they need to be compatible with pullback, right? So are compatible. With pullbacks. In the obvious sense, so if you have morphism of varieties, you need to have a commutative square. I don't know. That the thing. And this is the pullback, and then theta. Okay. Right, so this is a commutative, and again, as you are probably, you know that in this setting, you have it's really a structure, right? And we are giving, I would say, a homotopy somehow to making this commutative, and there are higher things and so on. Right. So this is what is somehow the right hand side of this equivalence. So it's somehow one should think about this as saying that this somehow kind of complicated object is not so complicated. It's given by this kind of a classical. I don't know. I mean, a priori, we don't know anything about this. We don't know that this is an affine group scheme, for example, right? So, yeah. So it's a consequence of this equivalence.
Right. Over which fields is this?
Which field?
Yeah.
Which fields over? You mean over which field I'm working? Yeah, it's over Q. So over Q.
Or any number field, I guess.
I mean, it's over Q, so it's over anything over Q. It's actually over the sphere spectrum. I mean,
sorry, no, I mean the motives. The motives are over which field? Like over the complex numbers?
No, I mean there are two fields here. There is the field K, which I fixed from the beginning, and then there is the coefficient field. But the coefficient field is you can take to be Q, or
but I just mean with
spectrum.
With K, like what Belyi realization are you taking?
K is a subfield of the complex number.
Oh, okay. Thank you. That's all.
Joseph, we have a question in the chat from Amalende. So I can read it out so that everybody hears it. So is it enough to consider only smooth schemes in this family?
Yeah, it is enough. Yes, it is enough. Yeah, there are some there are some flexibility in the choice of the domain of this functor. Yes, that's true. Yeah.
Thanks.
Okay. So I wanted to say something more about this. Oh yeah, let me say this. There is in fact a nice corollary of the proof of this theorem, which I want to also to state. So maybe before let me make a definition on is it really a notation. So yeah, so since this Motivic-Galois group is acting on these categories and in a way which is compatible with pullbacks and therefore also with push forward and so on, it's kind of natural to look at the following thing. So let us define. So I write sheaf geometric and I put here G mod maybe. It's not a good notation, but and I want to define this to be just the category of fixed point under the action of the Motivic-Galois group. So yeah, maybe I think it's usual to write maybe I put an H here. So what is this? This is the category of infinity category of sheaves which are equivariant. For the action of the Motivic-Galois. Right. So again, informally, what does it mean? It means that you have to take a sheaf F on X, and for every element of the Motivic-Galois group, you want to specify maybe not G. So G is acting on the category of sheaf, so it makes sense to write GF, and then you want to specify an isomorphism between GF and F, and this has to be compatible as usual. Right. So this is it's a category, and in fact, so one has a functor. One has a functor. Functors between. Okay, I wrote SH, but okay, let me take TM blank. So it's really functorial. So it's really natural transformation to these guys. Right. So it's you have some kind of yeah. You can enrich or you can refine the Belyi realization into functors. So definitely, if you take a motive or motivic sheaf over some base and you take the Belyi realization, in fact, you automatically land inside sheaves which are equivariant for the Motivic-Galois group. Right. So yeah, this gives such a functor, and let me say a few more words about this construction. So, for example, if you take X to be spec K, what happens? So the category of sheaves, yeah, this category I just introduced over K, this is in fact just category of representation of the Motivic-Galois group. So in some sense, it's just up to few things. It's essentially, it's morally, let's say, it is morally the category of Nori motive. And in fact, one should think about this this generalization over a base of this concept. I mean, this category over a base. One should think about this as a category of Nori motivic sheaves, right? So one could think, or one could consider this general. So over X as a category of Nori motivic sheaves. In fact, there have been at least 2 or 3 the definition of a category of Nori motives over a base by Arapura, by Ivora, and also by Ivora and Sophie Morel. So that but these are really kind of different in the construction. I mean, the construction is really different here. The objects are different. I mean, the object here are really sheaves with a structure, whereas in the case I just mentioned, I mean, for example, in the case of Ivora, it's really obtained as a representation of some co-algebra, if I understand correctly. But of course, one would expect that these categories are equivalent at the end. Do you take K rational representation or Q rational representation? Are you speaking about the coefficients? I don't understand. I hear. Yeah, it's over Q, on Q vector spaces. So there was a question in the chat. I answered this. I think about the coefficient of the representation. Okay, so I think that's all for this remark. The next thing I want to discuss is the following theorem. So it's really the same essentially statement as before, but now for
sorry, Joseph, before you go on, there's another question in the chat from David.
Yes, it's essentially. So should I read it?
Yes, please do that.
So David is asking, that's essentially because a Belyi sheaf on spec K is just a vector space, right? Essentially, yeah, it's a sheaf of geometric origin or not on spec K is just a Q vector space. All right, so let me state theorem 2. So again, it's the same kind of theorem. There is there's an equivalence of derived pre-stack, the group pre-stack. Between the Motivic Galois group and the group of auto-equivalences of the functor of local system of geometric origin, again with the tensor product. Okay, so yeah, it's of course you see it's a similar statement. Again, the right hand side is you should think about it as a collection of equivalences of this category of local system and which are compatible with pullback. So let me say a few remarks, in fact, about this second theorem. So again, we are, I think I said it orally, there is some flexibility. There is some. In the choice of the codomain, also the domain, sorry, domain of the functor And I heard something like recording in progress. I don't know.
Never mind, Joseph. Just go on.
Okay, I continue. So yeah, one can restrict to smooth varieties, K varieties, which are so-called Artin neighborhoods. So if you don't know what is an Artin neighborhood, it's not a problem. But this is a condition which implies that you are KP1. So that the homotopy type in the classical sense of your variety is just it's like B of some of its fundament of its pi 1. Right. So in this case, the category of local system on X is actually like it's a more concrete one. It's really the derived category of local system X heart. So it's a derived category of its heart, and the heart is a Tannakian category, right? And is a Tannakian category. And so in particular, it becomes a bit more, it becomes a bit more concrete. And so one could attempt to study the automorphism group of this Tannakian category and try to say something about the Motivic Galois group using this equivalence. Right. So yeah. So one could attempt. To directly analyze each of these groups, or the automorphism of local system on X, right? Not the whole functor, but and even maybe, yeah, let's see. One could analyze this directly and try to get some information on this, and then maybe try to use this to prove something about the Motivic Galois. So I will not give any really application in this direction. I'm still in the process of thinking about one application which go in this way. But let me give you one easy somehow way to deduce something interesting about the Motivic Galois group using this theorem. Right. So here's a corollary. So one can use this theorem to prove a Motivic version of Belyi theorem. So Motivic version. of Belyi theorem. So what is the statement is the following. So so here I have to take K to be Q. There is a more general version, but it's not as nice. So I just for simplicity I will take Q. Yeah. So the statement is that the Motivic Galois group, and here I want to really to take the classical one. So in the sense that maybe this. So I look at the classical subgroup. So it's like in derived like geometry, have a derived scheme. You can look at maximal classical scheme inside. So I do this. This is again, it's a group. No, this is a usual. It's classical affine group scheme. Right. So the statement is that this acts faithfully on the fundamental, the thing that write like this, pi1 geometric of p1 minus 3 point. Right. So what is this guy? I mean, this is by definition. This guy is by definition. This is the Tanaka group. So Tanaka group of local system on C minus 0, 1 of geometric origin. So this is why there is this geometric here. Okay. Right. So the analogy, I mean, you probably have seen the usual Belyi theorems. It says that the Galois group of Q bar over Q acts faithfully on the profinite completion of the pi1 of p1 minus 3 point. So this is really the analog of this. Let me just say very quickly how one can deduce this from the theorem. Improve. Right. So the idea is that essentially from what I have said here is that the classical part of the Motivic Galois group, of course, acts faithfully on if you want on the edges of this diagram, right? So this is you should think about this as some kind of a big diagram of maybe Tanakan categories, and somehow if you somehow therefore this guy is acting on the vertices of this diagram, and the action on the vertices is faithful, and in fact the various functoriality is somehow like defining equation in some sense that somehow cut down the automorphism of all these categories into this smaller thing. So in particular, this guy is acting faithfully on these categories. If you put them all together, this is like an immediate consequence of this here. Okay, so it's acting faithfully on the collection. Yeah, on these categories. And since I took the classical thing, it's not hard to see that in fact you can put you can put hearts here. Okay. Let's say for X heart in neighborhood. Okay, but then there is this easy or classical trick which based on the Lefschetz hyperplane theorem. So by Lefschetz hyperplane theorem, we know that if you take such an X and you take a general curve in X, then the map from the fundamental group of the curve would surject onto the fundamental group of X. But this is also true for for the geometric version of this, right? So using this, we see that we can restrict, we can assume the X's here to be curves, smooth curves. Okay. I think I need to drink some water. I'll come back in a minute. Okay.
By all means.
Okay. It's about. Okay, so there's a question in the chat. So the pi1 geometric is a Tanaka group of LS, geometric origin. So it should have a map from the usual algebraic Belyi fundamental group. Right, yeah. Which is free on two generator, exactly, yes. But how different do we expect the group to be? So I mean, this guy here, the geometric thing, is actually a pro-affine. So it's an affine group scheme, right? So it's of a different nature in some sense. But still, it's so you could ask, is it exactly the pro-algebraic completion of the free group on two generator? It's not the case, but it's yeah, it's a caution of that, but it's not the whole. This has to do with the fact that there are local systems which are not of geometric origin. Okay, so it's really a small caution of that. There are many local systems which are not of geometric origin. So you get a caution of that. It's and you yeah, it's just a caution. Does it answer the question, or do you want to say more about this? I mean, you can say something more, but maybe it's not the right place to do. Okay, so should I will continue then. Okay, so we can assume that the X is sure. I was curious which question, but let's go on. Yeah. Yeah. Okay, so the smooth curve, X is a smooth curve. Okay, so then then we use the classical Belyi theorem, which tell us that to find finite étale covers from these kind of smooth curves, which I can assume to be affine, maybe hyperbolic. Yeah. Okay, to P1 minus 0, 1, infinity. This is somehow it's a reformulation of the classical Belyi theorem that you can every hyperbolic curve affine can be mapped as a cover, I think, a tile cover of P1, finite cover of P1 minus 0, 1, infinity. But then this implies that the pi1 of geometric of X is a subgroup of, it's an open subgroup of pi1 geometric P1 minus 0, 1, infinity. In fact, the quotient is exactly has to do with the set with the fiber of this map from X. Anyway, so because of that, you see that if the action is already faithful on this guy, it will be also faithful on these guys, and therefore, is this what I wanted to say? No, sorry. The action is faithful on the collection of all the x's of all these guys, but yeah, but these guys are subgroup, so I think it implies what we want. Okay, so yeah. The next thing I want to say, yeah, okay, I think now I can start, yeah, second paragraph, which is about the proofs. So what was maybe the most surprising for me is how easy it is to prove these kind of theorems. So I will give essentially a complete proof of theorem one, and you see it's really once you know how to do it, it's not really not difficult. It just essentially it's combining two facts which were already kind of in the air, and so the second theorem requires more work, in fact, but in some sense it's the the surprise is already in theorem 1, in some sense, that this can be proved. Okay, so let me just tell you how one can prove this. So, right, so theorem 1 follows from 2 ingredients, which, as I said, were already kind of available in some form. Yeah, and the second one is actually very recent, but yeah. So let me tell you what are these ingredients. So the first ingredient. So this is maybe kind of probably many of you have know this in some form maybe is that is the following: is the fact that this category of sheaves of geometric type, geometric origin, is actually equivalent to the category of modules over this algebra B that I introduced before. This algebra representing singular cohomology in SH or Dn. So, let me say a few words about this. So, there is a functor like this. Right. So, in fact, right. So that the Belyi realization, in some sense, gives you this functor, and it's not difficult to see that you land in geometric type. So the fully faithfulness is an old observation of Szyczynski-Deglise. And in fact, it's a consequence of the fact that the Belyi realization is compatible with the 6 operation. It's not hard to find a proof when you know that, for example, that the Belyi realization, let me maybe call this B upper star as usual. So, for example, this would follow from the fact that B upper star commutes with internal homes on both sides. Right. So, this category here is monoidal closed. Similarly here, so that there are internal homes, and yeah, we know that the Belyi realization commutes well with internal homes, and then using the relation between internal homes and the usual homes, you get somehow the fully faithfulness here quite immediately. The fullness or the essential surjectivity, I think surjectivity, as far as I know, was not in the literature, but I think it was known to at least some people. I think it was known to Brad Drew, so I think it was known. So I found in some of his writing a remark saying that he's planning to prove this in the forthcoming work, and somehow he even somehow speak about the class, somehow the crucial point, which is the Lean semi-simplicity theorem. So I assume that he knew how to prove this, so I attribute this to him. And and here really the essential ingredient is the Leans. So this follows easily. Again, it's not difficult. Follows easily from the Lean semi-simplicity theorem for pure variation of Hodge structure. So I think Brad was actually working in the context of perverse sheaves, and he was actually he mentioned actually the more difficult theorem, the decomposition theorem of the Lean-Gaber, Bernstein, so the BBD famous theorem. But one can somehow actually use less, I think. Anyway, so yeah, the idea is that you so what you need to show here is really that so here you have a T structure, right? But by construction essentially, and you need to show that this T structure preserves the essential image of this functor. And this is at the end of the day you have to use something like the linear simplicity to do this. So remember, in the way I defined this, that there was like stability by kernels, for instance, and by the linear simplicity, kernels are actually exist, and they are actually defined by projector and so on. So it's not surprising that you need such a thing here. Anyway, so this is the first ingredient. The second ingredient is a recent result of Drew and Galois about the universality of SH. So this is universality. SH. Again, this is by Drew and Galois. Which essentially says that SH is like the initial functor from schemes to presentable monoidal infinity categories with some properties. And yeah, maybe I don't want to state the precise theorem, but this is the second ingredient. And then let me tell you very quickly how you combine these two and prove the results. It's really very simple. Maybe I will not give all the details, but it's really a simple computation. So remember, you are interested in understanding the, or I was interested in the automorphism of this functor. Now, by the first ingredient, this is the same thing as automorphism of SH, or maybe modules. Let me remove this tensor. So it's modules over the spectrum representing metric homology with values in SH. Okay, but okay, now there are some things to do here, but now you see the automorphism of SH is the identity, right? So here you use that automorphism of SH is trivial by the universality theorem of, and so in fact any possible automorphism is actually coming from B, and so you end up by some small computation, you end up with automorphism of B, and this was my definition, at least for the scope of the Motivic dialog. So this is basically the sketch of the proof. Okay, I still have 5 minutes. Let me maybe comment now on the second theorem. So as I said, the second theorem actually require more work, but in some sense, it's I would call this like maybe, yeah, it's like more standard things in some sense. So that there is less. I mean, it's just if you know what you want to do, you just do it, and then you take some time, but it's not super hard. Okay, so and the idea is that you want to, in fact, to deduce theorem 2 from theorem 1. So you will prove something like this. So the starting point is theorem 1, and then you go to theorem 2, and so more precisely, what you would show is that want to show that the automorphism pre-stack of the functor of sheaf or geometric type, geometric origin, this is the same thing as automorphism of local system. And for that, you need some kind of a machine which tell you how you could reconstruct general sheaves from local system. Right? So the idea is that to do this, you need a machine or way to construct let me say it like this: to construct the functor of sheaf geometric from local system geometric. And this is not so surprising. I mean, we all know that essentially a sheaf of geometric type or not necessarily geometric origin or not on some let's say a sheaf of geometric origin on a complex variety. You can always find a stratification of your variety on such that on each strata you have a local system, right? So it's not so surprising that you can write down a general sheaf using local system, and but somehow one needs to do this in a very coherent way, in some sense, so that you can, so that once you have, so in fact it's easy to find a map like this, right? So this is not difficult, but you want to go in the other direction, and so you have to say, so that if you have an equivalence of local of the categories of local system, which is functorial enough in all kind of morphisms of schemes, that you can use this to produce an equivalence, or to produce a family of equivalences on these kind of categories. And yeah, so this is some of the idea behind proving theorem 2, and but it's kind of quite complicated to make this idea work. So it's a simple idea, but it takes some time to make it work. And I still have 1 minute. I forgot to mention one important thing, is that so let me do it now. In fact, theorem 2 is a Motivic analog, or I think of it as a Motivic analog of a theorem of Pop, which was also conjectured, so previously conjectured. by Ihara-Matsumoto and Oda. So the classical version or the classical statement is about the Galois group, and so it takes the following form. It says that the Galois group of, let's say, k bar over k is equivalent to the automorphism of the functor that sends x to pi 1x. And what is pi 1x? Pi 1x, pi 1 bar x. This is by definition the pi 1 étal of x pulled back to k bar, and taken up to. So usually, when you speak about pi 1, you need to specify a base point. It's taken up to conjugation. You don't have to worry about the base point. All right, so this is the Ihara-Matsumoto-Oda conjecture. It was proven by Pop. In fact, he proved much more, and there are many things to say here, but I don't have time to do this. But the point is that this, the automorphism of this thing is really very similar to what we have here, right? Because of what I said here, right? So essentially, this category is completely determined by the pi 1 geometric, And an auto-equivalence of this category, of this Tannakan category, is essentially an automorphism of pi1 geometric up to conjugation in some sense. And so one can somehow compare these two statements a bit more. Okay, anyway, my time is up, I think, if I'm correct. So I would stop here, and yeah, in case you have questions, I would be happy to answer.
Okay, thank you a lot, Joseph. Let's all thank the speaker. Okay, the first question is in the chat from David.
Oh.
Is POP's result for any subfield K of C or just finitely generated fields K?
Yeah, POP's result actually works for any kind of field, even characteristic P. I think he has a version in characteristic P. Yeah, no, I mean, in characteristic 0, I think there is no it works for any field. Yeah, it's really for generative. I think the conjecture of Ihara-Matsumoto-Oda was actually, I think, only stated for finitely generated fields. So I think there was like the idea that this should be like an arithmetic result, and but it turns out that it's not. It's something which holds for any field. So it's even interesting. I mean, in the case of algebraically closed field, which then it's telling you that there is no automorphism of the right hand side, because then the Galois group is trivial. No, I don't know how to deduce POP from. So there is a small issue about base point that I haven't. I mean, I didn't try very hard anyway, but I think it's not so clear. So yeah. I mean, as I said, POP actually proved much more. So he has a lot of type of results. So he can, for example, he proved that the same result, but for very small categories of varieties. Yeah. So I don't know. I don't have a way to deduce POP's theorem from the Motivic version. And anyway, if I could, I would be only deducing a tiny part of this theorem. So it's yeah.
Okay, we have time for more questions. Anybody?
Yeah, I have a question about the last computation of Theorem 2. In Langland's program, sometimes a replacement of the Galois group is required. I mean, the Galois group of the fields. Is there any version or maybe thoughts about while Belyi group in this language? A similar computation of while Belyi group.
The while Belyi group.
Yeah, just for example, as you mentioned, of algebraically closed field, the left-hand side is trivial. Yeah, and if I clearly remember, automorphic forms over say if the base field, if we work over complex numbers, then the left-hand side group is replaced. I mean, the Galois group, which is trivial, is replaced with while the Belyi group, which is C star, I think, in this case. But anyway, it is very close to the Galois group, and I'm just wondering if there is an interpretation of this group in this language.
So let me see if I can. I mean, if I understand. So are you saying that are you saying that maybe there is some kind of version of this which would naturally give rise to the Belyi
while
the Belyi Motivic Galois group here?
Yeah, something
maybe.
Like that. Yes.
Maybe, I don't know. I mean, it would be of course very interesting, but so one thing huh?
Yeah, of course, it should be very interesting.
Yeah, but I mean, it should be interesting. But I mean, I don't know really what to put here. So I mean, I've thought about, you know, changing a little bit this guy here. So for example, you could, there is no reason to restrict to geometric to think of geometric origin, right? So you could a priori look at all local system, maybe with some condition on the monodromy at infinity. Like you want maybe the monodromy at infinity to be quasi unipotent, but anyway, you can enlarge these kind of categories. I mean, there are room for enlarging these category of local system, and then you can define some kind of a generalized Galois group, which would be the automorphism of the whole thing. This is a very interesting thing to do, I think. But to be honest, I don't. I mean, I have nothing really interesting to say about it. It could be, I mean, for example, I don't know if this guy would be really, I mean, it could be like, but by enlarging this in this way, you might somehow end up, you know, with a trivial group. There is no way to define, it might be that there is no way to define automorphism on all local system in a compatible way. Or maybe you get something very interesting, which is larger than the Motivic Galois group. This could have some, I don't know, maybe it could have some automorphic meaning. I don't know, maybe, but.
Well, so in the case of C or even R, right? This Veda-Linea group is going to be something like the Galois group of Hodge structures with real coefficients, right?
Is this is it? I don't know. I mean, is this?
Yeah, I mean, you basically get this twisted, well, this extension of Z mod 2 by this twisted algebraic torus. And so I guess one thing that's a little bit surprising to me is, so like if K equals C, this is saying that this functor has no non-trivial tensor automorphisms.
No, this guy here, even if K is equal to C here, this is still very big. The Motivic Galois group
right.
C is a huge, actually. It's not trivial.
Right, and there should be a map from the Veda-Linea group to this Motivic Galois group, which essentially corresponds to the Hodge realization.
Yeah, so the Hodge group goes to the Motivic Galois group. That's true. Yeah. And in fact, yeah, I mean, now that you mentioned this, actually, here's, I mean, it's an. So if you put, instead of geometric, you put Hodge, right? Here, something like you are looking at local system which are coming, which underlies, or which I don't know, which might underlie some variation of Hodge structure, right? So if you want, you look at variation of Hodge structure, but you forget about the variation and so on, and then you look at the local system, and then you build out of this some category. Then here, of course, you have the Hodge group that will map to that thing in a way which is compatible, of course. But then I don't know that this is an equivalence anymore. I suspect it's not an equivalence. Yeah.
When you say the Hodge group, you mean for integral Hodge structures or just real Hodge structures?
No, the integral one I was speaking. Yeah, but you can also do the real one, of course. But then you are over, you have a group over R. And
then it's just the linear torus.
Yes.
Which I believe is the.
But then I don't expect this to be an equivalence with that thing. I don't expect that. I mean, actually, it should not be. So the equivalence here is, I think, it's particular to motives. I mean, if you put I think Hodge structure, I don't expect this to be an equivalence.
Well, but actually, in terms of Pope's results, it would be interesting to see, like, let's say we took the unipotent completion of the fundamental group or something like this, which does have a Hodge structure. Then you get a version where you get the Vega group of R or C.
Yeah, I think I didn't get what you said at the end.
Sorry, so
what unipotent part of what?
So over the complex numbers, Pope's result implies that the functor that gives the profinite fundamental group has no non-trivial automorphisms.
Right. Yes.
But if we instead took something like the pro-unipotent completion of the fundamental group that does have non-trivial automorphisms simply by the fact that the pro-unipotent fundamental group has a Hodge structure on it.
Right. Yes. Yes. Exactly.
And so then you could ask a sort of a version, whether a version of Pope's result is true in that setting, like say over C, where we take just pro-unipotent or something like that, and then we consider the Ling torus or the Hodge-Galois group.
Yeah. I mean, you could also, of course, again, you could replace this by the unipotent part of it, right? You can also look at unipotent local system instead of all geometric local system. Yeah, but I don't know. Again, I don't know that it's an equivalence, but maybe it is. Yeah.
I think that would be like a version of the question asked about doing it with vague groups.
Why?
Well, because representations of the vague group of C are basically just Hodge structures with real coefficients.
Okay. But they are not. What is the link with unipotent local system? I don't.
Oh, just because unipotent, the fundamental group actually has a Hodge structure on it.
But it's also true for this guy here.
Right.
This guy is also. I mean, the pi1 geometric is also. It has also a Hodge structure.
Oh, so maybe
the O of pi1 geometric has a Hodge structure.
So I guess it would be if you take Pope's theorem and replace pro-finite with algebraic completion.
Yeah, this is what you get exactly. Yeah, this was my last remark.
Okay.
Yeah, I mean this guy is really representation of the pi1 pro-algebraically completed, a quotient of it, because again I'm only looking at geometric. At local system of geometric origin, so I cannot take the whole pro-completion.
Yeah.
Pro-algebraic completion, but only part of it.
And so actually, if you take the whole pro-completion, then that would probably have an action of this Hodge-Galois group.
No. If you take the pro, I mean, if you see, I think the pro-completion, the pro-algebraic completion is too big. There are quotient of them, which I mean, there's a quotient which has to do with Hodge structure. So you could call it, I don't know, pi1 Hodge if you want, and the further quotient is this pi1 geometric. And
right,
it's simply because not all local system can carry a Hodge structure. That's the reason. It's very simple. But if you look at all local systems that are coming from variation of Hodge structure, this will give you a Tannakian category which has some fundamental group which will be a quotient of the pro-algebraic completion of the pi1. This guy will have a Hodge structure, this quotient, but not the whole pi1 algebraic. This will not have a Hodge structure, at least not one which is natural.
Right, but the Hodge part surjects onto the pro-unipotent completion.
Yeah, that's true.
Yeah. So that's why I have to be cautious.
Questions today. There's one more question from Amalendo in the chat. Maybe I can read it out. So he's asking if you can explain a bit more how one patches up automorphisms of local systems to find automorphisms of geometric sheaves. In particular, is there some particular crucial underlying step?
Yeah, it's right. So what would be okay? Let me. I don't know if I can try to say some words about this, but okay. So the idea is that there are maybe let's say two. The maybe first step is the following: is to remark that if you know how to so. You can consider X which has a stratification. So you can X with a stratification. Let's say with a nice stratification. So By nice, I mean, let's say induced by a normal crossing divisor, for example. That is a smooth variety with a normal crossing divisor, and then you just give you some stratification on this. And then you can look at, I don't know, put S here to say it's stratified. Right, so this will be the category of sheaves of geometric origin, but which are local system on each of these kind of strata. Right, so this is a subcategory of. Okay, so somehow you start by saying by showing that it's enough to construct equivalences of these categories, and this is not hard. It's because if you work for the CDH topology, essentially any local system, any sheaf on X, you know, if you have a sheaf on X, you can find a CDH cover of X, and then on the cover you can find some nice stratification, which with this property that on the strata you get local system. Okay, so you can. It's enough somehow to construct equivalences of these kind of categories, which are compatible with all possible pullbacks and so on. And then you want to go from here to local system, and then, this is maybe the harder part. It's about, you know, understanding how you glue local system to get a general constructible sheaf. So the idea is that you want to write. Right, so the idea is to write this category as a limit. So limit in the sense of infinity categories of things of local system of local system on some well chosen Y's. And this can be done. The Y that will appear are essentially some kind of normal bundles of strata in X. So some kind of open subset there. And so there is some kind. That is, I mean, yeah, it uses this formalism of nearby cycle somehow to define functors between all these categories, and then you show that there is some diagram. You take the limit of this diagram, you end up getting exactly this category of sheet. So it's not any. I mean, it's something which is quite. I think it's a quite classical idea that you can build a constructible sheaf out of local system with some gluing data, but you have to say what are these gluing data, and you put them in a way which you can use coherently in some sense. Yeah, I don't know if this is if this answers the question. If you want me to say more about the specific point, I could try also. But
I think that's great, Joseph. Thanks a lot. I think that's it for today. So